Hello friends, this is 8th part in haloalkanes and haloarenes. In our former session, we have studied about nucleophilic substitution reactions, and that was only the introductory part. Why haloarenes are less reactive towards nucleophilic substitution reaction when compared to haloalkanes. And in the last session, we got to know that haloarenes are less reactive towards nucleophilic substitution reaction due to high electron density. This was the most prominent reason, because of resonance structures, because of difference in the hybridization of carbon atom, and because of instability of phenyl cation, and also due to high electron density, we understood that haloarenes are less reactive towards nucleophilic substitution reactions. Now, what happens when there is high electron density on the benzene ring? If the benzene ring has got more electrons on it, it has got more electron density on it, then it implies it carries a negative charge on it, and a negative charge means a nucleophile center or nucleophilic center. So the incoming nucleophile, which is also an electron rich species, which also carries negative charge, will not so easily attack electron rich centers, that is the benzene ring. For this reason, due to very high electron density on benzene ring, haloarenes easily do not undergo nucleophilic substitution reactions. To substantiate this explanation, we shall see one example how haloarenes are less reactive. Consider the example of chlorobenzene. If chlorobenzene is made to react with sodium hydroxide, if it is made to react with sodium hydroxide, then you know, if this nucleophile is to be replaced, if this nucleophile is to be replaced by this nucleophile OH, then the product we shall be guessing is phenol plus NaCl. For this reaction to take place, you need a temperature of minimum 350 degrees Celsius and at a pressure of 300 atm. This reaction also goes by the name Dow's process. It is also called Dow's process. Now in this reaction, you notice that whenever chlorobenzene is reacted with sodium hydroxide, phenol is obtained under these conditions, that is 350 degrees Celsius and at a pressure of 300 atm. Now, while you write the resonance structures for haloarenes, especially chlorobenzene, you noticed that the negative charge always appeared at two positions. Let us see this example. Again, once again, resonance structures. You will notice in these structures that the negative charge appears for the first time in this position. Okay. Then again in the next structures, you will notice that the negative charge appears at this position. This position is called ortho and this is para. Then the other resonance structures show that the negative charge appears once again at ortho position. Once again at ortho position. And finally, the resonance hybrid gives you the same original structure as we saw in the first one, that is here. Now if a nucleophile has to attack chlorobenzene, if a nucleophile has to attack chlorobenzene, then the benzene ring should become electron deficient center. For a nucleophile to attack benzene ring should become deficient in electrons. For this to happen, you need to remove the excess electron density present on benzene ring. You notice that in these structures, the electron density is more at ortho positions. twice at ortho positions and once at para positions. To explain how this affects the reaction, let us see. If the same chlorobenzene is substituted at para position by an electron withdrawing group like nitro group. The electron withdrawing group is nitro group. If this is made to react with sodium hydroxide, then the product will be same as it is here, NO2, which does not change. Here comes OH. The only difference is that this time the temperature will be around 170 degrees Celsius. How is this reaction different from the first one? In the first one you had only chlorine group and the temperature required was 350 degrees Celsius. This time one nitro group is attached at para position, the temperature almost decreased to half. Let us see one more example. If the same chlorobenzene, this time with two substituents, two nitro group, two electron withdrawing group at ortho and para positions, if this is made to undergo the same nucleophilic substitution reaction by sodium hydroxide, this time the product would be same. Wherever chlorine was there, you will get OH, phenol. Here NO2 as it is, here NO2 as it is. Again difference is in terms of temperature. The temperature again decreased. Finally, if the same chlorobenzene, this time with all the ortho and para positions blocked by NO2, if this example is used for nucleophilic substitution, then what would be the commonly guessed product? It should be OH, here NO2, here NO2, here NO2. The main difference is that in all these cases you utilized a strong base. This time you need not have even a strong base. Simply warming with water is enough. Simply warming with water will give you the desired product. So what do these four reactions indicate? This first one, second, third and fourth. What do these four reactions show us? It shows that as the number of electron withdrawing groups, that is nitro group, it increases. See, there was no electron withdrawing group in this example, therefore the temperature conditions are 350 degrees Celsius. Once one electron withdrawing group is attached at para position, the temperature decreased to 170. There are two electron withdrawing groups, temperature again decreased to 95. There are three electron withdrawing groups, you simply need to warm, that too without any strong agent, that too without any strong alkali. So this implies that electron withdrawing groups have a very influencing effect on the reactivity of nucleophilic substitution reactions of haloarenes. How is this possible? You see, while writing resonance structures, the negative charge, that is electron density, always appeared at ortho, para and ortho positions. If these positions are blocked by an electron pulling group, withdrawing group, that is nitro group. So this nitro group, if it is present at para position like in the first example, whenever this electron density appears at the para position, that electron density is taken away. It is taken away by the nitro group. As a result, benzene becomes electron deficient center. When it has less number of electrons, then the incoming nucleophile can easily attack benzene ring for substitution. Similarly, when there are two nitro groups, say from here the electron density appeared at ortho, here if nitro group is present, it pulls away the electrons. Second time again it appears at para, there again it pulls the electrons. Third, it appears at ortho, here also if a electron withdrawing group is present, if this also pulls away the electrons, then benzene becomes much more electron deficient, making it very easier for nucleophilic substitution. Therefore, whenever an electron withdrawing group is present at ortho and para positions, the reactivity of haloarenes towards nucleophilic substitution reaction increases. If an electron withdrawing group is present at ortho and para position, the reactivity increases. What happens if the same electron withdrawing group is present at meta position? I mean at this position. Notice that in the resonance structures, the negative charge never appeared at these two positions. If I number this as 1, 2, 3, 4, 5 and 6, it never appears at 5 and 6. The negative charge, that is electron density, never appears at 3rd and 5th positions. Therefore, when a nucleophile has to attack, and if there are no negative charges here, even if you attach an electron withdrawing group there, it has got no effect on the reactivity. Therefore, presence of an electron withdrawing group at ortho and para positions increases the reactivity of haloarenes towards nucleophilic substitution reactions, whereas if the same electron withdrawing group is present at meta position, then no effect on reactivity is observed. In other words, reactivity decreases. This was about nucleophilic substitution reactions of haloarenes. Now we shall see the second set of reactions they undergo, that is electrophilic substitution reactions. Electrophilic substitution reactions of haloarenes. You might have studied about electrophilic substitution reactions and their mechanism in your first year syllabus. You have studied nitration, chlorination, then sulphonation and Friedel-Crafts reaction. Similarly, this year we have for haloarenes, they are electrophilic substitution reactions. They are very easier when compared to nucleophilic substitution reactions. Simply looking at the substituents present on the benzene ring, you can decide what kind of electrophile substituted product you are likely to get. Now, a minute before you saw in the resonance structures that negative charge appears at ortho and para positions. This means if chlorine is present on benzene ring, it increases the electron density at ortho and para positions. Means these two positions will have more number of electrons, or electron density is more at ortho and para positions. This means whenever an electrophile is what? It is simply a species which is positively charged or which is neutral, but it is electron deficient. So electron deficient species are likely to attack those places where there is surplus of electrons, where there is excess of electrons. And where is excess of electrons in this chlorobenzene? At ortho and para positions. Therefore, whenever chlorobenzene or in general any haloarene undergoes electrophilic substitution reactions, you are likely to get two products, ortho and para products, because chlorine is a ortho para directing group. You have studied about directive influence of functional groups and substituents in the first year. Based on that, you are supposed to remember that halogens are ortho para directing groups. This means whenever halogens are present on benzene ring, they ask the incoming groups to come and attach on the benzene ring at ortho and para position. Let us see one example. The first example is halogenation. If you are taking chlorine, then chlorination. How is this reaction done? When chlorobenzene is reacted with chlorine. To avoid confusion, I shall take same chlorine only. In the presence of anhydrous AlCl3 or anhydrous ferric chloride, any of these as a halogen carrier, then what two products are to be obtained? One should be at ortho, the other should be at para. So you will get two products, that is one ortho dichlorobenzene and para dichlorobenzene. You can write in this form, or else you can write their IUPAC names also. Then you removed hydrogen once from here, once from here. Therefore, 2 hydrogens are lost. So 2 HCl. 2 benzene rings are there. Therefore, 2 chlorobenzene. A total of 1, 2, 3, 4. Therefore, you use 2 chlorines. Now, in this example, it appears very simple, and it is. In this example, when chlorobenzene reacts with chlorine in the presence of anhydrous aluminum chloride or anhydrous ferric chloride as a catalyst or a halogen carrier, you will get 2 products, orthodichlorobenzene and paradichlorobenzene. You can identify which product is major. Always remember, if 2 groups, whether same or dissimilar, if 2 groups are present very nearby to each other, adjacent to each other, lesser the gap between the 2 groups, then repulsions between them would be more. When repulsions are more, stability will be less. Stability less means the quantity of yield obtained will be less. For this reason, always para is obtained as a major product and ortho is obtained as minor product, because in para the 2 groups are as far apart as possible. They are very far. So for this reason, repulsions between them will be minimum. Hence, para product is obtained as a major product and ortho product is obtained as a minor product. Understood? Now let us see the second example, which is nitration. In nitration, the same chlorobenzene, it is reacted with, for nitration you need a nitrating mixture. What is nitrating mixture? A mixture of concentrated nitric acid and concentrated sulfuric acid. A mixture of both concentrated nitric acid and concentrated sulfuric acid is called nitrating mixture. When chlorobenzene is reacted with nitric acid in the presence of sulfuric acid, you get 2 products. Those 2 products should be, here chlorine as it is. Out of these, always practice this method. While you are writing a reaction, whichever product is formed as major, you are supposed to write that in the beginning. Do not write in this fashion. So the major product should be para-chloronitrobenzene. Minor should be ortho-chloronitrobenzene. Remaining water molecules. Simple. Similarly, sulphonation can be done. Similarly, sulphonation is done. How? When chlorobenzene is reacted with. For sulphonation, you need only sulfuric acid. You do not have to use nitric acid again. In the presence of sulfuric acid, you will get 2 products. Para-chlorobenzene sulfonic acid and ortho-chlorobenzene sulfonic acid. Out of these 2, which one is major? Para is always a major one. Here also para product is major product. So you studied 3 electrophilic substitution reactions: halogenation, nitration, sulphonation. Let us study one more. It is Friedel-Crafts alkylation. It is Friedel-Crafts alkylation. In this, it looks similar to halogenation or chlorination. Here chlorobenzene reacted with chlorine. Instead of chlorine, you write methyl chloride, CH3Cl. These reagents remain same. They act as catalyst or halogen carrier. So what product is obtained? Preferably use anhydrous aluminum chloride to avoid confusion. So this time you will get 2 products again. One is orthochlorotoluene and parachlorotoluene. Which one is major? Para. So you are supposed to write para in the beginning and ortho in the second time. The remaining is same. You have one more Friedel-Crafts reaction, that is called Friedel-Crafts Oscillation. If you use methyl chloride, if your intention is to insert, if your intention is to incorporate methyl group or alkyl group in the benzene ring, then it is alkylation. If you want to introduce acyl group, then it is Friedel-Crafts Oscillation. Friedel-Crafts Oscillation. Same chlorobenzene is reacted with acetyl chloride. Earlier you used methyl chloride in the presence of anhydrous AlCl3. This time you use acetyl chloride, anhydrous ferric chloride. Try not to use aluminum chloride, use ferric chloride only. The reason is because many a times chlorobenzene will react, this methyl chloride will react with the catalyst used. So avoid using aluminum chloride and use ferric chloride. So product will be COCH3, acetophenone, and the same acetophenone, once at para and the other time at ortho. Okay, out of these two major, one is para. You got para chloroacetophenone and orthochloroacetophenone. So how many electrophilic substitution reactions are there? There are totally 5: halogenation, nitration, sulphonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. COCH3 or CH3CO, this group is called acyl group. If acyl group is to be introduced into the benzene ring, the reaction is called acylation. Since it is done by these two fellows, Friedel and Craft, therefore it is called Friedel-Crafts oscillation. If your intention is to insert alkyl group, preferably methyl group, then the reaction is called Friedel-Crafts alkylation. Do not get confused. If in the exam they ask you, explain the Friedel-Crafts reaction of chlorobenzene, you are supposed to explain any one of them. If they very clearly specify, explain Friedel-Crafts alkylation, then use only the first reaction. If acylation, then the second one. And then we have come to the last part or last reaction. It is reaction with metals. It is reaction with metals. Haloalkanes also reacted with metals. Can you remember which two metals were there which reacted with haloalkanes? They were sodium and magnesium. With magnesium, haloalkanes formed Grignard reagents, and with sodium metal they underwent Wood's reaction to give you alkanes. Here we have the third set of reactions is reaction with metals. We have only one metal, and that is sodium metal. The first reaction. What was Wood's reaction, you remember? When a haloalkane reacted with sodium metal in the presence of dry ether, this part was lost. So you got alkane. You got alkane, isn't it? What if one haloalkane remains same, one haloalkane is replaced by a haloarene? Similarly, you see, you have one haloalkane replaced by a haloarene. Remaining part is same, sodium metal as it is, plus one haloalkane. If this is done in the presence of dry ether, you will get, what will you get? You replace this much part. If this is gone, you will get 2NaX, and here you will get R. This reaction shows that a haloarene and a haloalkane are reacting with sodium metal in the presence of dry ether to give you alkyl benzene as a product. Alkyl benzene as a product. This reaction is called Wurtz-Fittig reaction. Often students make the mistake of writing the name Fittig as Fitting, I-N-G. It is wrong. Fittig is the name of a scientist. It is to be written as F-I-T-T-I-G. This question is an important question from exam point of view. Often this question can be asked in various forms, like they will give you the reaction, you are supposed to identify the name of the product, or they leave only this much part blank, you are supposed to fill in the blank and identify the name of the reaction. If two haloalkanes are used with sodium metal in presence of dry ether, the product is an alkane, the reaction is Wurtz reaction. If one haloalkane is used, one haloarene is used along with sodium metal in presence of dry ether, the product is alkyl benzene and the reaction is Wurtz-Fittig reaction. The reaction is Wurtz-Fittig reaction. Let us see how Wurtz-Fittig reaction is done using an example. See, a haloarene is reacting with sodium metal along with a haloalkane in the presence of dry ether to give you alkyl benzene as a product. Let us see one example. If the same halobenzene is done as chlorobenzene, reacts with sodium metal along with methyl chloride in the presence of dry ether. Dry ether is compulsory. If you do not write dry ether while writing reaction, this reaction has got no value. Without dry ether, the reaction will not proceed. The product is, how do you guess product? Eliminate this much part in the form of NaCl. What remains should be attached to the benzene ring. You will get toluene, not toluene. It is to be pronounced as toluene. How do you prepare toluene? Using chlorobenzene by Wurtz-Fittig reaction. How is it done? When chlorobenzene is reacted with methyl chloride along with sodium metal in the presence of dry ether, toluene is obtained. There is one more reaction. The second reaction is this one. Now you know what Wurtz reaction is. Wurtz reaction is the one wherein two haloalkanes react with sodium metal. If one haloalkane, one haloarene reacts with sodium metal, then it is Wurtz-Fittig reaction. If two haloarenes react, no haloalkane appears. This time only two haloarenes react, like this. Say this is one haloarene. It is reacting with sodium metal and another haloarene. Just to avoid confusion, I am writing in this fashion so that removal becomes easier. Okay. Then what product is obtained? The same reaction in the presence of dry ether. You will get this product whose name is biphenyl or diphenyl. Both are same. Sir, what if I write X here? That can be done. Look, if chlorobenzene is reacted with sodium metal in the presence of dry ether, what product is obtained? I did this so that you attach easily. Remove this much part, then you will end up with same product biphenyl or diphenyl. This reaction wherein only two haloarenes are used, this reaction is called Fittig reaction. This reaction is called Fittig reaction. In Fittig reaction, two haloarenes react with sodium metal. In Wurtz Fittig reaction, one haloarene and one haloalkane react. In Wurtz reaction, two haloalkanes react. Do not get confused because all the three are very important from all competitive exams point of view and even your theory exams. So these three questions, that is Wurtz reaction, Wurtz Fittig reaction and simply Fittig reaction, these three will be one of the compulsory questions in your question paper. Either they can ask you directly, explain Wurtz reaction with an example, explain Wurtz Fittig reaction with an example, or explain Fittig reaction with an example, or else reaction will be given, reagents will be given, you are supposed to fill the product part, name the IUPAC name, give the IUPAC name of the product and name the reaction. 3 marks question can be in this way, or else you will be given in the form of a statement like chlorobenzene and methyl chloride react with sodium metal in the presence of dry ether. What is the likely product to be formed? 1 mark. Write the reaction, 2nd mark. Name the reaction, 3 marks. Understood? So all the 3 questions are important from exam point of view. They are Wurtz reaction, Wurtz Fittig reaction and Fittig reaction. I already told you that whenever named reactions appear, they are all important. Now, after all these 3 reactions, the next part in the chapter is only a very small bit, that is uses of haloalkanes. That simply you can study from your textbooks easily. You do not need any explanation from it. So this was all from haloalkanes and haloarenes chapter. I hope you have followed these classes and understood. In the next session or in the next classes, we shall study one more chapter from organic chemistry, that is alcohols, phenols and ethers. Thank you.